There we go. Some questions about fixed point math. And this is one of the top topics that came up on yesterday's Sunday session. And it comes up on most of my Sunday sessions. We talk about fixed point and how in memory fixed point is represented. And then we go into then how floating point and floats and doubles are represented in memory. And I tried to emphasize how important fixed point numbers or that number representation are on embedded systems because of the somewhat often lack of a floating point unit. And if you don't have hardware to handle the floating point operation, so whether that be adding or subtracting or multiplying, dividing, whatever it is with regards to a floating point number, if you don't have the dedicated hardware for it, it becomes very slow if you need to emulate that on your general purpose processor. So instead, we can use fixed point math. And the whole goal of fixed point numbers and fixed point math is to take advantage of the fact that your processor is already good handling integers. It's already good at adding, subtracting, multiplying, whatever it is, integers. So how can we represent a number that has a fractional component in a way that we can still use normal integer operations on it? So I'm going to go through a little bit of code. I'll try and write up some code that is some common fixed point operations. And once again, in different interview contexts, depending on what the position is, this may be more or less important. But for a lot of embedded positions and a lot of embedded interviews, this is kind of expected that you at least know what it is and potentially how to use it. And in many cases, it would even be expected to be able to write the kind of code that I'm sharing here. So first, when it comes to fixed point, we need to define where our point is. So if we have, for instance, an 8-bit integer, or an 8-bit, let's call it a data structure, we need to reserve some of these bits for the whole number component and some of the bits for the fractional component. And we can put this decimal place, if you will, anywhere we want. I think oftentimes in my examples, I place it right there in the middle, but we really could put it anywhere we wanted. And obviously this is here just 8 bits, but we could have 32 bits, 64 bits, any number of bits that we want to hold both our integer and fractional components. So let's just, for the sake of keeping things clear, let's define a macro. Let's just call it shift. And this macro is going to be, where is our decimal place? So for these examples, I'm going to assume that we're using a 32-bit type, or 32 bits to hold our numbers. And we're going to place the decimal point in the middle. So 16 bits from the least significant bit is where we're going to divide the whole number component and the fractional component. And for the sake of hopefully not confusing people, let's also create a Typedef so that when we're reading and writing code, we can be reminded that we are dealing with a fixed point number, not an integer. Because once again, we're going under the hood, everything is being stored as an integer. From the compiler's perspective, from the processor's perspective, we're just dealing with integers. We as the programmers are the ones that are especially treating some of the bits versus other bits. So let's just create, let me try, normally I write in all uppercase, but let's try creating a new type called fixed. Just we can use this from now on. So when it comes to the fixed point, at least formats that I've been talking about so far, we can do addition and subtraction just as if they were regular integers. So if, for instance, we have like a fixed x And I'm going to get to what these equal to in a second. But the fixed y, we can add these two fixed numbers together just with a regular plus sign. And this, once again, is one of the benefits of this particular way of, or this particular common way of defining and using fixed point numbers, is that this sort of addition and subtraction can just occur without needing to do any other special math. To create these fixed point numbers in the first place, once again, I talked about the kind of the conceptual number and then the in-memory representation. I tried to differentiate that those two don't necessarily have to be aligned in terms of how you might normally think about a binary number. So the conceptual number that we might be talking about could be 5, but we are going to store that number in fixed point notation. And in order to do so, we need to shift that number by 16 bits. The 16 that we defined up here. So conceptually, well, let's assume we have the number 1, make it easy. If we have the number 1, we need to make sure that we shift that 1 up to here so that it continues to be part of the whole number component, as opposed to the fractional component. So creating, if you will, a fixed point number first involves that shift. And then similarly, if we have some other number we're trying to add, we will similarly shift the number by those 16 bits. So addition and subtraction, very simple, very easy. Of course, in order to have something like this, both x and y need to be in fixed format. So we need to do this operation first on both of them in order to add them together. We couldn't, for instance, just say x plus y if y is simply the number 10. Then it won't do what we would presumably want it to do. The number 10 in a fixed point notation would be all fractional. Well, mostly fractional. In this case, we have a 32-bit number, it would be all fractional. And what we want is that 10 to be a whole number component. So we have to make sure our numbers are in the proper format, but once they are in the proper format, then we just add them together. Multiplication is a little bit more complicated, but hopefully just as simple from a computational perspective. And first, let's look at a decimal example, and then we can kind of extrapolate that to binary. If we have the numbers 10.00 multiplied by 10.00, just once again, ignoring fixed point just kind of conceptually, we're trying to multiply the number 10 by 10. In fixed point notation, we get rid of that decimal place logically, and all we stored in memory is these numbers, 1,000 times 1,000. And 1,000 times 1,000 is 1 million. But what we wanted to do is do 10 times 10. So we expected the number 100 as the result, or 100.0, or 100.00. But if we simply were to multiply them in the same way that we added them here, if we just did x times y, we would get something somewhat absurd, like 1 million as the result. So what we have to do when it comes to multiplication and division is after we do the operation, we need to kind of fix it up, if you will. So what we've noticed here is that when we multiplied our integers, our decimal place is no longer in the right spot. We started off with the decimal place right there, such that we had 2 places to the right of the decimal place. And if we were to just put that same decimal place here, such that there was 2 to the right, well, we're not at 1 million, but we're still at whatever it is, 10,000. So what we need to do whenever we multiply 2 integers or multiply 2 fixed point numbers, we need to divide by the shifting factor, or divide by that scaling factor. So after we've done this multiplication, we then need to divide it by however much we shifted it in the first place. So let's look from more from a kind of C perspective instead. If we were to define a function like int32 multiply, where we take in, let's make these things all, yeah, let's we define this nice new type of ours. Now, fixed multiply fixed fixed A, let's say, and fixed B. We are trying to multiply two fixed point numbers, and we want the result of this function to be another fixed point number. And I just said that we can't just do A times B, because then our decimal place, if you will, is in the wrong spot. What we need to do now is fix up where that decimal place is supposed to be by shifting the number by our scaling factor, or dividing it by our scaling factor, equivalently said. So we have our A times B, and then we shift that by 16. Now we can return that result. So to say it again, in order to multiply two fixed point numbers, we do the multiplication, and then we have to divide them or shift them by that scaling factor in order to make sure that the final result has the decimal place back where we would expect it to be, such that the whole number component and the fractional component are logically correct. There is one bug in the line I just shared here. When we multiply A times B, we get a very large number. We get a number considerably larger than the conceptual numbers that we were starting with. And then we are shifting to fix that up. What could potentially happen here is A and B, even if they're only moderately large, once you multiply them, could be so large that they no longer fit in the 32 bits that we specified for those variables. So we were overflowed as a result of that multiplication. And then when we shift back, we no longer have what we would expect from that multiplication operation. So the most typical way you would fix this is, instead of doing this first line, you would instead cast each of those to 64 bits first. So uint64a times uint64b, and then shift that accordingly. And that gives us that extra space so that our considerably large number after that multiplication has some wiggle room, so that when we shift back, we land back in our 32-bit data space. This is if we're multiplying two fixed point numbers. So A and B here are both already in fixed point format. This fix-up, this shifting fix-up, this division fix-up is not necessary if you're multiplying by a constant. So if we have fixed A equals, let's say, 5, and we want our result is also a fixed point number, we can simply say A times 5. And that will logically take the value of A and multiply it by 5. So we don't need, there's no need necessarily to convert this 5 into a fixed point number itself before doing the multiplication, in the way that doing the addition up here did require both operands to be in fixed point format. So addition and subtraction, both operands need to be in fixed format or in standard int format. And in the case of multiplication, only one of them needs to be in fixed format if all you want to do is a basic multiplication. Any questions at the moment? In practice, what you would typically see a lot of these things represented as is just a header file full of macros. And the macro says multiply, divide, converting between different formats. Here I said that we will always have 16 bits as our decimal place. But there's no requirement that it always be 16. So oftentimes, whether it be a function or a macro, there would be an additional parameter that specifies, well, what was the scaling factor? So, oh yeah, go ahead.
So for the adding both number, when you're doing a shifting to 16, wouldn't if they're getting if they're a huge number and they get added and they become a very huge value, right? That can be more than 32 bits. So
exactly. So in the same way that you have to worry about overflow when you're, let's say, adding two regular integers together, it's possible that the sum of those two integers is larger than the data type that you've allocated to store it. The same thing can happen here in fixed point addition. Your X and your Y could have been large enough such that adding them together overflowed and effectively, well, could potentially truncate the ultimate result. So fixed point kind of has the same concerns, if you will, on that front as any other sort of regular integer operations. It ends up being slightly, I don't want to say more dangerous, but most people think about, oh, like if I have a number like 1,000 and I multiply it by some other reasonable number like 1,000, that'll probably fit in 32 bits. Like people just have this mindset of like what numbers just naturally fit in different data types. But when you start dealing with fixed, especially if it's not entirely clear what that shift is, you run into these overflow issues a lot more commonly just because you're not thinking about it. You're not in that same mindset. So what some people would do, whether it be a macro or a function, is add some checks here, for instance, to check whether or not overflow would occur and take some appropriate action, log an error or search something because of that. So that is certainly an option. One other upside of having this all be kind of a macro style is when you're using fixed point, let me take a step back. When you're using fixed point, you have to be very intentional and careful with regards to where you decide to put that decimal place. If you put it too far to the left, you can no longer store particularly large numbers. If you put it too far to the right, you don't have very many bits available to represent the fractional component, and hence your resolution ends up being significantly smaller. So you have to be very intentional for where you put that decimal place. And you need to have a good understanding of what data it is that you're dealing with when you make that sort of decision. So you're not typically going to say, oh, for this entire code base, or for this entire system, we're only ever going to use 16, for instance, as our decimal place location. It might be data to data, or structure to structure, or case by case where that decimal place gets placed. But one upside of using something like a macros for this is that if you decide, I don't know, 6 months from now, oh, you know what, I actually would have preferred a different bit location, then, well, it's easy to just change that one line of the macro to update where your decimal place ultimately lives. And I've seen that come up also in the context of interviews where people write code that has these magic numbers like 16 hard-coded all throughout their implementation. And then at some point, as they're working through that task, they come to the realization, oh, 16 actually wasn't the right number to choose. I need to change it. And then they have to go through and change their magic number everywhere and hope they got it in all the right places, and all the issues that come out of that. So writing code that's kind of flexible like this allows you to adjust your decisions in the future without having to rewrite everything.
Thanks, Glenn.
And then just once again, just to be clear, in an interview, in an embedded interview, being asked to write this function or write similar sort of functions or macros is a totally reasonable question someone could ask you. I would say that is fair game in the context of embedded interviews where the expectation is that your position will be working on a chip that doesn't have a floating point unit or may not have a floating point unit. Okay. Oh, yeah, sorry, go ahead.
So on the fixed of y, let's say the value that given. So can I assume the 5 and 10, it's always a UN 16 bits, so that when I shift, I would assume that it's not going to overflow. In this case, it turns out to be a different value, and I would be adding 2 different value here.
Yes, I think it's safe to assume that that's going to be 32 bits by default. If you wanted it to be, say, 64 bits, you would, you'd put long after it to indicate that you want it to be a long type, in the same way that you might indicate it to be a float or an unsigned with F or U. So you can make that distinction there to make sure it doesn't overflow as well. Well, sorry, not that it doesn't overflow, but yeah, to your question.
Okay, thanks.
Glenn, I have a question.
Sure thing.
The equivalent fraction portion, are we ignoring in this multiplication? Like, for example, if you take 100.23 and 98.53, something like that, if you are multiplying both of them together, maybe that fits in 9.7 format actually. 9.7, 9 bits for integer and 7 bits for fraction.
Mm-hmm.
So if you multiply both of them in 9.7 format, so what do we do with the, or how do we multiply the fractional numbers?
Yeah, so this function that I have here, sorry, and I guess this is something I didn't say earlier. Maybe I implied it, but didn't explicitly say it. For this function to work, A and B need to be in the same format. So in your example, 9.7. So on my original example, 16.16. They both need to be in the same format for this for this particular function to work. You could obviously make it work, but you have to change the function if they had different types. But in your case, if it's 9.7, then this shift macro right here, rather than being 16, would just be 7.
Mm-hmm. What about the fraction results? I mean, the fraction part also, if you multiply, that also will have some values, right?
So the beauty of fixed point multiplication is that you don't have to multiply, that you as the programmer don't have to intentionally multiply the whole number component separate from the fractional component. You can multiply both of those the complete fixed point numbers. You can multiply those together as a whole, and the fractional and whole number component will be maintained.
That small result is negligible because it is not even, it will not even cross maybe, I don't know, cross the 1.0 or something. It won't even cross the integer value of 1. That's why.
So you're asking if you had, so if you had numbers like 0.1 times 0.1, let's say.
Yeah, like for example, 100.23 and 98.23. If you multiply the 0.23, right? That fractional results, I think, if you multiply in calculator, that won't contribute much actually. The 0.23 fractional results.
Yeah, and I might be misunderstanding your question, but the thing here is in your example, we have, oh, I already put 0 there. So let's say we have 90 and 100, 90.1 and 100.1, and we're trying to multiply those two numbers together. In this fixed point multiply function below, A represents 90.1, B represents 100.1. And if you see in the actual math, all I'm doing is multiplying 90.1 times 100.1. I'm never isolating just the fractional component or just the whole number component for that multiplication. So this 0.1, when it is multiplied by 90.1, this 0.1 is going to apply to the entirety of 90.1, not just to the 90.1's fractional bits. Did that answer the question, or am I still maybe misunderstanding what you're asking?
Yeah, I think that's a good answer. I got it. Mm-hmm.
Cool. And just to kind of bring this all back together, we always have a conceptual notion in our mind of numbers, 5, 10, 90.1, like that's our conceptual idea of the number. Maybe like when we think about it in our head, that is the number. But when we write it down on paper, when we put it in memory in a computer, however it is that we're storing that number, we're not storing the same thing that was in our head. We're doing some sort of translation from our head to paper, our head to the computer. And there is an infinite number of ways of representing the number 5. And we could number 5 like that. We could represent the number 5 like that. We could do it in some other let's call it language entirely. There's many different ways that we can write down the number 5, but they all refer back to the same concept of the number 5. And the same way in the computer, we could represent the number 5 by 0, 0, 1, 0, 1. Yeah, we could represent the number 5 that way in binary, but we could also have chosen any other arbitrary way that we wanted to represent the number 5. And we've obviously talked about fixed point, we talked about floating point. There's a multitude of other ways that we can represent in memory the conceptual number 5. And there's many reasons why you might want to choose one of those different ways over other ways. We talked in particular about fixed point versus floating point. We also talked very briefly in the past about variable length encoding. They all have a slightly different way of encoding or storing a conceptual number in memory. And there's pros and cons to each one of those different approaches. The reason why fixed point, or at least fixed point in the way that we've been talking about it here, is so popular and widely used is because it takes advantage of what your processor already provides in the context of integers. If we had chosen some other totally random way of representing the number 90.1 in memory, we might not have been able to do something as simple as just A times B. We might have had to do something like isolate the whole number, isolate the fraction, and do some long involved process of multiplying all the different components together. But because we've chosen this fixed point format very intentionally, we get all of these things kind of for free, or at least for cheap. So I kind of want to emphasize that there is other ways that one could do fixed point, could represent a number in fixed point, and there's maybe pros and cons for those different forms. This happens to be the most common way, at least in my experience, for doing this.
Glenn, could you give maybe an example, just maybe something like for two numbers 4.3 and like some other number 10 point something, and add them, or just show how it's represented?
Sure. I mean, we can take the number, we have the number 5 right here, and then we could take the number 10. I believe that's 10. 1, 2, 4, 8. Anyone objects to the top number being 5 and the bottom number being 10?
So this includes the actual number 5, or it is some fraction? Like how do you conceptualize?
Well, I'm gonna get to that in just a second. So let me you bring up a good point. I'm kind of skipping a step, and I'm skipping it intentionally. But let's just, for the sake of argument, pretend that we're not talking about fixed point at the moment. Any objections to the top number, this top binary number being the number 5 and the bottom number being 10? I got that right? Okay, and then when we add these together, we get the number 15, correct? I think we're all in agreement there, that this addition worked correctly, and this is what the computer would do as well for these 4 bits. I've only defined what four of the bits here. So, and then once again, you wanted an example of addition. If I were to add 4 more bits here to the right and say, you know what I actually was doing was adding these 2 8-bit numbers. These components on the right all add up to 0, of course. And now we end up not with the number 15, but we end up with some considerably larger number. Correct?
Yes.
And now let me relate it back to fixed point. Fixed point is all about saying we have agreed that we're going to put the decimal place in a particular location, and anytime we want the conceptual number back, we have to do a shift. So let's just say I put the decimal place here, the decimal place here, and the decimal place here. So what I started off at the beginning was not the number 5. I started off with 5.0, and I added to it 10.0, and lo and behold, what I get is 15.0. So I realized there was no non-zero fractional component to these numbers, but what I just demonstrated here was the addition of 2 numbers in fixed point format. So then you might ask, okay, well, what about the fractional component? Let's just erase, let's say, 2 of those zeros and say that what it actually was not 5.0, but 5.2. This would be 5.25, I think. I frankly don't do this sort of math regularly, so I wouldn't be surprised if I got something wrong. But let's say that's 5.25, and this other number now is 10.125. Now that I've changed these numbers here on the right to make them non-zero. And then when we add the 2 of them together, we get...
Hey, Glenn.
Yep.
I was just curious, like if we take a simple example like 5.1 and 10.9, so there will be an overflow as well, right? I mean,
Yeah,
9 plus 1. Yeah, go ahead. I was just curious, how would that be represented? Because 9 can be represented 1001, and then 1 would be represented 01. If I have 5-bit representation, that will not overflow into the fix on the whole number part, right? So anyway, sorry, go ahead.
Yeah, no, we can do an overflow example in just a second. But we see here is now when we add these 2 together, we still have 15 as the whole component, and we now have 0.0110 in the fractional component, which would be our 375 down there. So yes, there's a whole number component and a fractional component, but when you do an addition like this, it doesn't really matter what's the whole number and what's the fractional part. The decimal place stays in the same place, and numbers might happen to well, not overflow, but like flow one way or the other. So let's look at the 1.5 example. 0001.1000 This should, I think both of these should be 1.5, because this is going to be 2 to the 0th, and this is going to be 2 to the minus 1th in terms of their kind of positions. So we are adding these 2 numbers, 1.5 and 1.5, and what we would expect is 3.0, right? That's conceptually what we would expect out of this. So we can add these up in the same way that we would add any other regular addition. in this, for kind of starting at the rightmost bit and going to the left. So 0 plus 0 is 0, is 0. 1 plus 1 is 0. Carry the 1. 1 plus 1, 1, 1, 1 added together is 1. Carry the 1. 1, 0, 0 is 1. And then 0, 0. So what number do we end up with? Lo and behold, it's the number 3, just like we expected.
So, Glenn, when you started this, how do we declare a number like 5.25 as a fixed?
Let's take that 5.25 again, and let's just organize it. Let me write it down here again so it's clear. So
Hey, Glenn, sorry to cut you off, but on the previous example, I just wanted to finish how the 5 got represented as 1 followed by 3 zeros.
sure.
5 is 101.
Let's remember. I'll answer both your questions at the same time. And actually, yeah, let's actually do people who were with me yesterday probably saw a similar example already. But let's say we have the number 5.625. Ignoring binary, let's just say we have a decimal number 5.625. What is this number actually? It is 5 times 10 to the 0th plus 6 times 10 to the minus 1, 2 times 10 to the minus 2, and 5 times 10 to the minus 3. Like if we were to distill this number into these 4 components, 5 times 10 to the 0th, so 5, 6 times 10 to the minus 1, and so on down the line. So for a decimal number, we can, hopefully everyone can see, we can fairly easily divide it up into these subcomponents, if you will. We can do the same thing for binary. So let's look back over here at this example of 5.25. What we have here is 0 times 2 to the 4th plus 1 times 2 to the 3rd plus 0 times 2 squared. Oh, nope, sorry. Started 1 off. One times 2 to the 0th. 0 times 2 to the minus 1. 1 times 2 to the minus 2. 0 times 2 to the minus 3, and 0 times 2 to the minus 4. And to make this even more clear, this one is here, that one is there, that one is there, that one is there, and so on down the line. So I have distilled the original number into its individual components. And what I wrote out here is no different than what the typical person, if they see a binary number, they're like, oh, like 2 to the 0th plus 2 cubed plus 2 to the 5th adds up to be this numbers. I'm not doing anything special. The big difference I'm doing here is I'm going to exponents below 0. So we have 2 to the 0th, and then the number below that is 2 to the minus 1. So we get 5.25, and sorry, we get the 0.25 specifically because we have 1 times 2 to the minus 2th. So we have to get 1/4 because of that. And I think you asked the question of how do we get 1.5? So this right here, that 1 up there is 2 to the minus, in the 2 to the minus 1 position. And 2 to the minus 1 is, well, 1 divided by 2. And 1 divided by 2 is 1/2, which is the same thing as 0.5. So
yeah, makes sense. Thank you.
Yeah. So, and this is a good question. So, and I've said it in different ways, and maybe each person, maybe each time I've said it, hopefully it's helped a different person. But this fixed point number is taken as a whole. We are never, well, at least in the example so far, we're never saying, okay, this is the whole number component, and this is the fractional component, we're never saying that those are two unique numbers. We're treating it together as a whole, and that's how we have this kind of system we have going over here. So it's still always, each position is 2 to the somethings, and it happens to go negative on one side. It's not like we magically reinterpret this as yet another integer such that we have 2 to the 0, 2 to the 1, 2 squared, and 2 cubed, for instance. And this is kind of one distinction, well, kind of a distinction between fixed point and floating point. Remember, for floating point, we have the mantissa and the exponent, and both the mantissa and the exponent are the kind of their own unique representations of a number. So they're both in that typical, let's call it 2's complement, kind of binary representation of a number, both the mantissa and the exponent, and they're independent from each other. They both start at 2 to the 0th, if you will, and move on over for each of them. But for fixed point, we have our 0th exponent, and then things go negative or positive either direction from there.
Right. So when we declare, right, like a fixed A is 5, we always do a left shift. So won't we always get 0 in the decimal part?
Yes, you're absolutely right. If we take the number 5 and we shift it to the left, then you're absolutely right. We're going to end up with a conceptual point 0, 0, 0, 0, 0 in the fractional component. And that's exactly what we wanted, because what we wanted was the conceptual number 5. We wanted the number 5.0. So it is exactly what we intend when the fractional component ends up as all zeros.
Right, but when it is not all 0, then how do you declare? Like, how do you declare?
So your question is how? Your question is, let's say we have the number 5.5. So let's say we start off with well, we write 5.5. So C interprets this as a floating point number. Like if you write something with a decimal place, C just assumes that you have you're trying to use a float. Your question is, how do we convert this to fixed point? Right?
Yes.
Okay. So to do that, let me define it as a macro to make it have one line. And let's call it float to fix. That's conceptually what we're doing. So what we want to do is take our 5.5 number and as a float, and ultimately have something that is in fixed point format. And we can obviously do the same thing backwards as well. So what we need to do here is let me think about this for a second. I was just thinking about it the other way around, and I realized I need to convert it from float to fixed. We need to multiply this number by we need to multiply this number by a large number such that we get both the whole and fractional component to be shifted over. So we take x and we multiply it by 1 shifted over by, let's say, 16. And then we need to cast this all, I should have put the cast in there, cast it all to a uint 32. Yeah, so we need to multiply our starting floating point value by a large number, but based off of our shifting, based off of where we've placed that decimal place, multiply it by a large number so that we essentially get rid of this fractional component from the float, and all we have is a whole number. And then we can, from then on, treat that as a fixed point number. And then likewise, if we wanted to go back the other way, fix the float, we would do somewhat of the inverse. We would take X, we would cast it to a float, and then we would divide that by 1. And once again, I'm assuming that we're put in decimal place at 16 here. Obviously, this could be some other number. So we have our X that was a fixed number, cast it to a float, and divide it by our large number to convert it back to a floating point number. Cool. Sorry, thanks for bearing with me. I had to kind of think through the logic and math there a little bit. And I'm pretty sure I got it right. But